Hi everyone, this is Mr. Youngren, and I'm going to walk us through Unit 2, Lesson 5. To start, we have an opener, so what I'm going to ask you to do is actually hit pause and work through this. Even if you're not sure, it's always a good recommendation just to give it a try, and then once you have something on your paper, go and hit unpause, and then I'll talk you through what you should have done. So go ahead and hit pause, work through it. I'll see you back here in a second. All right, welcome back, and here are the answers to the 3 opening problems. Let's just quickly recap what's going on here. So I like to use different colors. I know it's kind of hard to see on this recording here, but anytime that we see something inside these parentheses, like what we're seeing on this first opening problem and the one off to the right here, we need to take the original x's in the equation and replace them with what's inside parentheses. So what I always explain it as if we're taking this x in this equation, we're picking it up and we're throwing it out. And when we throw it out, we're creating space for something to come in and replace that. So over here, when -1 is inside those parentheses, this is saying replace that x with -1. And you'll notice the parentheses there. That's really important because it helps us keep track of the order of operations. So once I have -1 in for x, all we're doing is working on this right side, simplifying it down by using our order of operations. So squaring -1, -1 times -1 is +1, and then times 4 is 4. 4 minus 16 gets us to -12. So what this means is that when x is -1, the y value or the output is -12. And let's come back to this middle one. And over here, same idea, except now instead of replacing the x with -1, I'm replacing it with the whole term of x plus 3. And so we're actually creating a new equation. And that's going to lead us into what we're doing today, actually. So I created this space. Everything else is the same. So you'll notice I still have the 4. I still have the square. I still have the -16. The x is just changing into x plus 3, which we have here in parentheses. So what's in the parentheses should always match up with where the x's used to be. Now, just like over here, order of operations matter. So when I go to simplify this, I need to square the x plus 3, which means to multiply x plus 3 by itself. I do want us to get in the habit of writing this out, because otherwise we try to take shortcuts and sometimes we make mistakes there. So x plus 3 times x plus 3, we need to distribute or FOIL. A lot of us have learned to FOIL this way using boxes. So if you needed a box, no problem. It's just x plus 3, and that takes care of all your multiplying so that you end up with either x squared plus 3x plus 3x plus 9. Those would be all your insides. And after I add the 3 x's, that gets us to 6x. So x plus 3 squared is equal to x squared plus 6x plus 9. Finally, we'll distribute the 4 that was in front of that x plus 3 squared, making these terms 4x squared plus 24x plus 36. And we still have that -16 at the end. So after adding those two numbers, we end with 4x squared plus 24x plus 20. All right, and then this middle one, a little bit different because it's asking find x when g of x equals 0. What I'm thinking about here is I'm like, okay, what is this saying? G of x is this whole equation, right? That's what it equals. So essentially, I'm taking this g of x in this equation, I'm picking it up and I'm throwing that one out. And I'm going to go ahead and put 4x squared minus 16 where that g of x used to be. And that's what you're seeing here, where I have 0 equal to 4x squared minus 16. And then we're just solving. So trying to get the x squared by itself. And then once we have that by itself, get x by itself. So I added 16 to both sides. If it's minus, we've got to do the opposite. Divided by 4. And then that gets the x squared by itself. And then from there, I'm going to take the square roots. Square roots undo the squaring. And remember, if we're taking square roots, there's always going to be 2 answers. It's plus or minus 2. That's because 2 squared is 4, and -2 squared is also 4. So you're getting 2 answers there. All right, now, like I said, this is essentially what we're going to be doing today. And the name of these are called compositions of functions. So let's go ahead and jump down to these notes. Let's fill these out, go through a couple examples, and then get you all on your way. So we can substitute anything into a function. That's what we explored in the opener. And even another function. That's what we kind of saw over here on the right problem. When we say evaluate g of f of x, you want to substitute f of x into the x of g of x and simplify. So what does that mean? That means we're taking the whole equation of f of x and plugging it in for the x's in the other equation. Once we get to some examples, that'll kind of make sense. Right now, I just want us to focus on, when we see this, what does it mean? It's going to mean take f of x, replace it for the x's in g of x. And then we got to always remember to simplify. So there's going to be a decent amount of algebra here. Now, we want to make sure we're reading these correctly. So when you see something like this, it reads as g of f of x, and it can be written in a few different ways. It can be written just like what you saw up there, so g of f of x, or you might also see g and then this weird circle kind of thing. It looks like the letter O. That's actually called the composition operation. So this is g composed with f of x, which means we're going to take f of x and plug it in for the x's of g. Now, an additional thing we're going to do besides just finding these functions is we're going to look for their domains. When we do this, we immediately need to find the domain of the original functions. And the reason that is because we are limited by those domains. So when we're making new functions, whatever the domains of those originals are, we got to keep those values and hang on to them. And then we're going to add in the domain of the new function we create. So the composite function. So we're having to check for domain probably 3 different times, depending on what f of x and g of x are. Now, we want to make sure that we can identify the input. This is kind of like what we talked about, where if we see h of p of x, that means take p of x and substitute it into x of the h of x function. And down here, where we see g composed with w of x, it's always the inside function getting plugged into the first function. So this means we're going to take wx and substitute into the x of j of x. All right, now, as we go through this, and after we see an example, I want you to come back and take a look at this page, because without something to refer to, this might just look like a whole nother language to us. But let's take an example, and then I'm going to encourage you to flip back through and actually see if you can kind of make sense of what all this is after doing this with a couple examples here. So if I have f of x equaling 2x plus 3 and g of x equaling 4x minus 16, we need to first find the domain of each. Now, when they're equations, we need to think about what are the domains of each individual functions. You might want to look back at Unit 2, Lesson 2, where we have that whole page and the domains of each function. So when I look at this, these are both linear. Because they are linear, their domains are negative infinity to positive infinity for both. So with any new function we create, we don't have any domain restrictions right now. We'll see an example, especially when we get down here and see the square root, where we're going to have some restrictions before we even create new functions. So we're good to go. Let's start to find both f composed with g of x and then also g composed with f of x. So first, what this is saying is we need to take g of x and replace the x's in f of x with that whole function. Now we can write this in a couple different ways. We know what g of x equals, right? G of x is this whole thing, 4x minus 16. So one way that we can think about this is we can take f, and instead of composing it with g of x, we can compose it with what g of x equals. That's 4x minus 16. Now, if you look back at the warm-up problem, this should look familiar, right? Where I'm going to take f of x, so this original function, and I'm going to keep everything the same, except where the x used to be. We're going to pluck that thing out. We're going to create some space, and I'm going to add in whatever's in the parentheses here. So right now, this is the same thing as f of x. The only thing I've done is I've removed that x to create some space for g of x, which is 4x minus 16, to come in and take its place. G of x represented by the green, f of x represented by the blue. And all we need to do is simplify. So I can distribute this 2, which means to multiply. So it's 8x minus 32, and we still have the plus 3. So after I combine those like terms, I get 8x minus 29. And so how we would write this is we'd say f of g of x is equal to this new equation, which is still linear. And the domain of that function is also negative to positive infinity. So domains weren't much of a factor here. All right, I'm going to actually ask you to hit pause here and see if you can find the opposite. See if you can find g of f of x. So same process, but now instead of taking g of x and plugging it into this x, we're going to take f of x and plug it in for x and g. So go ahead and hit pause, see what you come up with. Just put something down, and then we'll check back in a second. All right, well, here's what you should have. Once again, I imagine that I start with g of x, which is 4x minus 16. And I'm going to pretend as if I picked that x up off the page, I threw it out and created a bunch of space. In that space, we're going to replace that x with what the original function for f of x is, which is 2x plus 3. And so I have 4 times that 2x plus 3 minus 16. After we distribute, I have 8x plus 12 because we are multiplying and combine like terms to end with 8x minus 4. And once again, we're ending with a linear function. So the domain is negative to positive infinity. All right, well, there are the basics. We're going to jump to one that's a little bit more complicated, and especially with the domain. So let's do one more together, and then I'm going to let you all work on the rest of this lesson in your groups or on your own. All right, so we need this first by thinking about the domains here. Let's do the easy one, which is p of x. I recognize that equation as being linear. I know that every domain of a linear function is negative to positive infinity. Now with this function, that is a square root. And one thing we talked about in class is square roots cannot equal negative numbers. So we need to figure out what's the smallest value of x that we can plug in to where we're not taking square roots of negative. We're going to always find that by taking the inside of the square root, which is that x plus 3, set it equal to 0, and we're going to solve. So I'm minus 3, get x equals negative 3. If I plug in negative 3 plus 3 is 0, and we can take the square root of 0. So the smallest number that works is 0 itself, and then we can take any positive number from there. So 0 to infinity. We are restricted by this domain. So because we're saying, oops, not 0. Let's fix that, Mr. Younger, negative 3. Because we're saying that the domain of this function is negative 3 to infinity, any new function we create that involves h of x, these are the only numbers of x we can use. So basically, we can pretend that this domain doesn't matter. We are restricted by what we have here. So any new function, the smallest number that can work is negative 3. And there's a chance we might even have to eliminate more numbers with our new function. Okay, so, but at the very least, negative 3 is the smallest number that will work for both of these functions. All right. Let's jump in and find the compositions where I have h of p of x. So again, we can think about p of x being 4x plus 5. So really what I'm looking for is h, and instead of p of x, I'm going to write down what it equals, which is 4x plus 5. And so then I'm going to go back to h of x. I'm going to write down the whole equation, except for where the x is. We're going to pick that x up. We're going to throw it out, create some space for something to come in there, and work on simplifying. So where that x used to be, I'm going to replace that with 4x plus 5. So in green, that's our p of x, and now we can work to simplify. Notice I did put it in parentheses. That's just good habit. Lots of times there won't be anything for us to do in there, right? I don't need to do anything with 4x plus 5. So the parentheses don't matter, but it is a good habit that anytime we're plugging something into an equation, that we include those parentheses in case there's something we need to do. So really I can do 5 plus 3 to get 4x plus 8, and then plus 7 on the outside. So let me just clean that up because I made that a little bit big. 4x plus 8, and then plus 7. So no difference between these two lines. I just wrote a little too large. And so our composite function of h of p of x is equal to this new square root function. So now we said our domain was negative 3 to infinity for h of x. We want to find this domain as well and see if we are further restricted by this value. So really, let's find this domain and revisit. So once again, just like we talked about up here, I'm going to take what's underneath the square root, that's 4x plus 8. I'm going to set it equal to 0, and I'm going to solve for x by minusing 8 first. dividing by 4, I get x equals -2. So in this new function, this is saying the smallest number that works is -2. So for this function, the domain is -2 to infinity. We need to also consider the original domain of h of x, which was -3. Now, -3 is a smaller number than -2. So really, the domain that is taken over is this new one. We can't take any numbers below -2 for this function. So when we first arrived here, we said the smallest number that works is -3. But now, because of how our composition function worked out, we are now restricted by this -2. So our full domain is -2 to infinity. So we actually could have just gotten away with just finding the domain of this last function. Okay, but we just kind of got lucky there. We still need to check the originals. All right, that domain piece is definitely a little complicated. So be patient with it. Think about it, and we can always ask questions once I get back. All right, just like we did last time, I'm gonna have you hit pause, and I'm gonna have you work on number 4 on your own, and I'll have your solution for you when you unpause. All right, a little bit different here, and there's a lot going on. So let's first talk about the composition part, because that's really the main focus here. Some of these problems are gonna have some real messy algebra and some things that we need some refreshers on. So the composite is us taking p, or excuse me, h of x and plugging it in for the x of p. So again, I take what h of x equals, which is this whole square root function, and notice that I'm putting that in the parentheses, because now that's signaling when I bring down the p of x function, so 4x plus 5, I'm gonna keep everything the same. So we've got the 4 the same. The x has been picked up and removed with a bunch of space next to where that x used to be, and we're still adding 5. So once we have -3 times x plus, or square root of x plus 3 plus 7 in for that x, we now need to simplify. The distribution here, we actually are only going to distribute the 4 to the -3 and to the 7. That's because we only distribute into terms separated by plus or minus signs. So this -3 is being multiplied to the x plus 3. So I don't want to multiply 4 into both these terms. That would be over multiplying. We don't want to over multiply. So we're just distributing to the terms separated by the plus sign, which is the -3 and the 7, making this -12 times square root of x plus 3, and 4 times 7 is 28. And after I add 28 plus 5, that gives me 33. So that 33 is on the outside of the square root. So if we look at what we have for our composite function, we're still taking the square root of x plus 3, just like what we originally had in h of x. So when I go to find the domain of this new function, we first were restricted by -3 to infinity, but then this hasn't changed. So our domain is actually going to stay the same as -3 to infinity. All right, and then that's it. So be patient with this lesson. It can take some time, and notice that having different colors can help. Okay, take one function, do everything with that in one color, and another function in another color. It really helps us to kind of see how all these compositions play out. All right, let's see what we got ahead. We got some group practice, and this is where I'm going to actually let you all go. So I want you to complete the group practice in your groups. Remember, there is an answer key on Schoology for this entire lesson, so you'll have to scroll down to page 31 to check it. And then once you're done with that, you need to complete the independent practice on the following page, and then that'll take care of everything. And make sure that you're checking the answer key, not copying the answer key, but just checking. All right, everyone, thanks for listening, and have a great rest of your day.